Howdy guys, Jimmy Song here, off-chain. I spoke at the Hong Kong Bitcoin meetup last night, and I gave a presentation on Schnorr, BN, and Musig. These are all signature schemes, and a lot of the people said that they first of all like the slides, so they can sort of understand what the hell is going on, and second, they encouraged me to make more content that's technical on YouTube, and I was like, these don't necessarily get a lot of views, but I did want to at least think it's important that some of these technical advancements are sort of put into a good place, or at least known about, or at least marketed or something. And so I wanted to just briefly go over the presentation I did yesterday and talk about that. Yeah, I think I pissed off a bunch of people yesterday. Like all the yeah, and let's talk about music as far as I can talk about it. All right, so let's go to the different window, and hopefully you guys can see this. So basically, this is Schnorr, Bellare-Neven, and Musig signature schemes, and I'm going to go through it a little bit. And in order to really understand what the hell's going on with the other signature schemes, you really have to know something about ECDSA. And if you're not familiar with elliptic curve math, first of all, you can take my class and I'll teach you all of it. But if you don't, then just know a few things about how it works. So P equals EG. E is your secret key, P is your public key, G is the generator point. The big thing is that this is asymmetric. If you know E, you can get P pretty easily. If you know P, you can't get E. And more or less, this sum here, Q equals EG plus PP, can really only be manipulated if you know how the two are related. That is, you know the secret, or E. And that is based on the difficulty of something called the discrete log problem. It's the inability to invert, get E from P, more or less. But you can go in the other direction. If you know E, you can get P. Anyway, verification for ECDSA is, pretty straightforward. You have R and S. In general, when you see any sort of signature scheme, they almost always give you two numbers. R is sort of something random, and S is kind of like the signature. You're almost always signing a hash that's interpreted as a number, and you have to call the key of the person that signed it. Anyway, the way this works for ECDSA is that you have to do a bunch of field division. And you might not be familiar with what that is, but let's just say that it's kind of expensive from a computational standpoint, especially for large numbers that we deal with SEC-P256.1. So U equals Z divided by S, V equals R divided by S, and then you do that summation from the previous intuition. And if the result has the same R, same X coordinate as the thing that you computed before, or the thing that you used at the beginning, then the signature is valid. And a lot of signature schemes kind of do this. You sort of prove that you can manipulate it by using the result as part of the calculation. So you can see that V equals R divided by S, and you use V in the VP portion. And if you're using R, then you know that you as a signer are saying, okay, this is what the result's going to be, and I'm going to prove it by putting it in as part of the calculation. And then it comes back to the same thing. So you start with R, you end with R. That's common for sort of non-interactive signature schemes, and that's what we're doing here. Anyway, you can actually do the signing more or less straightforwardly. You have a secret. You have to sort of choose kind of like a second secret, this random number K. You have to be very careful not to reveal that. Otherwise, end up compromising your private key. You get a second sort of random number or secret, and you calculate sort of the scalar multiple point, and r equals x coordinate. And you use that r to calculate s, and it all sort of works out mathematically because UG plus VP, according to the definition of it, you end up getting, kg, which has r as the x coordinate. And this works because discrete log is known to be hard, and r is essentially used in the calculation to produce r. That proves knowledge of the secret, and that's more or less why this is very important. That's why the ECDSA works. Schnorr, sort of intuitively speaking, is instead of field division, we're going to use hashes. And it's, again, based on the discrete log problem and the inability to calculate hash-free images. But basically, it works very similarly, but instead of a signature with two numbers, you have a point and a number. And the rest is the same. You have a message and a public key. And instead of UG plus VP, you have SG minus the hash of RZP. And if Q is the same as R, the signature is valid. Again, you're using capital R as part of this calculation, and you come out to the same R. And that's, sort of like circling back, and that proves that you know the secret. Signing looks very similar, except, instead of just the x coordinate, we're taking the entire point, and S becomes this K plus H, the hash of the point and the message times E. And the signature is a point. R is sort of like the random point, and S is like what you're using to prove that you know the secret. And it works because of, you can go through the math later, but more or less a lot of the terms cancel because of how we sort of specified S, and you end up with capital R. So R is used in the calculation for R. R is in the hash of R concatenated with Z. So R is using the calculation of R, and that proves knowledge of the secret. And that's more or less Schnorr, right? Like this idea that you can utilize hashes instead of field divisions to do a lot of the work for you. Bellare-Neven is sort of like a general, if you want to do multi-sig, you can Neven. And the key aspect of Bellare-Neven is that you can aggregate signatures. So it still depends on, it still has the same sort of assumptions about discrete log being hard and hash pre-images being hard to calculate. But you can aggregate signatures. Currently in Bitcoin, each signature has to be sent separately. So you have R and S for every single pub key. Instead, we can aggregate them and have a single R and S, and that more or less works. So how does it work? Well, you have a signature, a message, and instead of one pub key, you have a bunch of pub keys. And you have to calculate this hash and this other thing, C sub I, and that's based on the hash. And you as a verifier know all the pub keys, so you have P sub I. You also are given R as part of the signature, and Z is the message. And then you calculate this thing, and if it's equal to R, it means the sig is valid, and also means that every single pub key had to sign it, which means that n such secrets are known. The way that signing works is that instead of a single EG equals P, you have multiple EI, and you have n such pub keys and n such private keys. And what you have to do first is calculate the pub keys of a whole bunch of stuff. And you have to, each person has to choose their own K sub I or some random thing and get the resulting random point. And R is just the sum of all of those R sub I's, or a point addition, more or less. And C sub I is calculated the same way, and S sub I is equal to K sub I plus C sub I, E sub I. And this sort of formula comes up over and over again, where you have KESA by and ESA by blinded by something, and that's what we more or less do. And the S part is also sort of an aggregate of all the S sub i's, and the signature being RS works, which is kind of incredible. And you can go through the math, but all of the terms cancel, and you end up with R. And R is used in the calculation to generate R and proves knowledge of every secret, not just a single secret. And you can do it in a much smaller fashion because you only have to send one R and one S. Pretty brilliant as far as I'm concerned. Musig is even more brilliant because you can aggregate not just the signature, but the pub keys. So instead of sending over n pub keys, you send over a single aggregated pub key. And again, it has the same sort of security assumptions. And the verification is exactly the same as Schnorr. And this is where it's really exciting. As far as the verifier is concerned, the verifier has no idea if it was a single private key or multiple private keys that generated the signature. There's no way to know. And that gives you a lot of privacy. It's a lot like sort of like threshold signatures that the Princeton people put out a few years ago. But you know, this is like very solid, and you can do it, I think, within 2 rounds and not 3. Anyway, same, very similar stuff. You have to choose, like, say, KESA by for each person. ESA by is the secret. R is the point addition of all of the R's. P is this, the aggregated pub key is this weird thing. Not exactly intuitive, but it's L and your pub key sort of concatenated. So each sort of coefficient to each pub key is different. And then C sub I is going to be this thing, and S sub I is going to look very similar, and S is the aggregation. And the aggregate key is P, and the signatures are an S, which is amazing, because now you've essentially signed this thing, and you can't know what you more or less sort of aggregatedly signed something. And no individual can do it. With something like Schmier secret sharing, the private key is like sort of produced, and then you sign sort of on a trusted machine. You never have the aggregate private key sort of computed anyway. It's a lot more like threshold signatures. And you can go through the math, but cancel as in the other ones, and you end up with R. And what's kind of crazy is that you created an aggregate key whose private key is only really known collectively, and that's kind of amazing. You can prove the knowledge of the collective secret, and nobody has to know whether it was from 1 key, or 2 keys, or 100 keys, and that's more or less why this is so exciting. We can gain privacy. We can you know, reduce expenditure on sort of any transaction, and you get multi-sig. I mean, you do have the drawback of having to interact, but you have to do that anyway with any sort of multi-signature. But that's more or less Bellare-Neven. And what we have here, and I wanted to sort of like talk about that at least a little bit, because that's something not a lot of people are familiar with. Anyway, yeah, I mean, I'm noticing that there aren't that many viewers, which is to be expected. It's a technical one. If we were talking about ICOs or something, I'm sure it would be thousands of people. All right, so what would be the advantage of having multiple public keys? I mean, you can distribute, like, you can make it like 5 of 9 and distribute 3 of them to one person or something like that. You can random interesting things like that. Anyway, hopefully that sort of describes for you what you know, I've been investigating, and hopefully it sheds light on why this stuff is exciting. And I do tend to geek out on this stuff, but you know, I know it's not necessarily like the thing that a lot of people are that interested in, but you know, hey, hopefully the people that are interested in it become developers. So thank you very much. and this song is